This is the next section that is on graphs, intercepts, and symmetry. So let's take a look at the top of your notes, and it says, recall, if the point AB is a point on the graph of an equation, then when x equals a and y equals b, the equation will be satisfied, meaning it will work and be a true statement. So let's look at example 1a. It says, determine if the following points are on the graph of the equation, and we're going to use 2x minus y equals 6. And we're given this point, the point 2, 3. So we're going to plug in this for the x and this for the y and just check it. So 2, take out the x, put in the 2, minus, take out the y, put in the 3. Is that equal to 6? Does 4 minus 3 equal 6? Not so much, so no, that point is not on the graph of that equation. Let's look at b. We've got the point 2, negative 2. We're going to check it in the same equation. So 2, take out the x, put in a 2, minus, take out the y, put in a negative 2, being very careful with your signs. Does 4 plus 2 equal 6? Yes, it does. So yes, this point is on the graph of the equation 2x minus y equals 6. Let's look at example 2. It says if the point 6b is a point on the graph of y squared equals x plus 3, what is the value of b? Well, here's the equation. Y squared equals x plus 3. So we're going to plug in this 6 for the x and then solve for what the b is. So we would say we're going to take out the y and put in a b. B squared equals, take out the x, put in a 6, plus 3. So b squared equals 9. Take the square root of both sides, and b could be 3 or negative 3. So what points are on the graph? That would give us the point 6, 3 and the point 6, negative 3. Both of those points. It's real important that you get both the positive and the negative root when you do it that way. All right, in the middle of your notes it says to graph an equation, either get the linear equation in slope-intercept form, y equals mx plus b, and use the slope and y-intercept, or create an xy table with at least 2 points. So we'll do it both ways on here. And the directions are to graph the equation in number 3, and we have y equals 2x plus 5. So let's first try it with an xy table, but then we're going to look at what we actually have in our equation. So I'm going to put, since it's solved for y, it's easier to pick values for x. So of course I'm going to pick 0. That would give me y is 5, because that term would go away. I'm going to pick a 1, then I would have y equals 2 times 1 plus 5, or y equals 7. Let's try negative 1. Y equals 2, negative 1 plus 5, or y equals negative 2 plus 5, and that would give me y equals 3. So we've got 3 points. That's good enough. So let's graph that equation. I've got the point 0, 1, 2, 3, 4, 5. There's that point. I have the point, I'm going to have to extend this, 1, 7, which is about right there. And then I have the point negative 1, 3. So there is my line with my points. Now, how else could we have done it? Well, the original equation was in y equals mx plus b form. This told me that my y-intercept was the point 0, 5. Okay, that's right there. We got it. And this told me my slope. The slope is 2 over 1, which means up 2, right 1. So starting at this point, I could have gone up 2, right 1, and I landed back on the line. Or I could have gone down 2, left 1, and I landed on the line. Because that would be a negative over a negative. So you could have used it either way. Let's look at example 4. It says graph the equation y equals x squared. Again, the easiest thing to do is, since it's solved for y, is to pick values for x. So if I let x be 0, y is 0. If x is 1, that would be 1 squared, y is 1. If x is negative 1, y is also 1, because it would be y equals negative 1 squared, or y equals 1. If x is 2, y is 4. If x is negative 2, y is also 4, etc., etc. So, let's look at what that graph looks like. I may have to go up one more. All right. So what we have is the point 0, 0. We have the point 1, 1, and negative 1, 1. We have the point 2, 1, 2, 3, 4, and the point negative 2, 4. And what you can see is our graph is in the shape of a parabola. Mine's not very good because I don't have a gridded coordinate plane. And if you don't believe it, you can pick a few more points to see what it's going to be. Notice, though, that y is always going to be positive, because when you square here, square the x, you're always going to get a positive y. So you don't see any values down here in negative y land. All right. Let's go to the next section, finding intercepts from a graph. Recall, intercepts are the points where a graph crosses or touches a coordinate axis. I am not going to attempt to draw this graph that you have in your notes, so you just need to look at your guided notes. For example, 5, it says to list the intercepts. So all we're going to do is just look at the graph and write down the points where it touches each of the axes or crosses. So the x-intercepts are where the graph crosses the x-axis. So the first one, starting on the left, is the point negative 3, 0. Then we have the point, it's about 1.5, 1.5. 0 is between the 1 and the 2, over there on the positive x-axis. And then we also have the point 5, 0. So the graph comes back around and comes up through that point 5, 0. So notice, all of my x-intercepts have zeros in the y spot. The y-intercepts here, where it crosses or touches the y-axis, we have the point 0, 3 up at the top. Then we have the point 0, negative 1. Then it comes back around and we have the point 0, negative 3. Notice all the y-intercepts have zeros in the x spot. So that brings you to that box. It says to find the x-intercepts, let y equal 0 and solve for x. To find the y-intercepts, let x equal 0 and solve for y. So let's do number 6. It says find the x and y intercepts of the graph y equals x squared minus 4. Then graph the equation by plotting points. So let's first look for the x-intercepts by putting a 0 in for the y. So this is the x-intercepts. So if I put a 0 in the y spot, I would have 0 equals x squared minus 4. You can do that one of two ways. You could factor it, difference of two squares, or you could move the 4 over and take the square root. We're going to move the 4 over and take the square root, so we get 4 equals x squared, square root of both sides, and x equals, remember, plus or minus 2. So you've got plus or minus 2. So there's actually two x-intercepts. It's the point 2, 0 and the point negative 2, 0. Those are my x-intercepts. Now to find the y-intercept, I'm going to put a 0 in for x. That's much easier. And I get the point 0 for x, y is negative 4. So if I graph that, I'm going to try to squeeze that one in right here. We have the point 0, negative 4. I have the point 2, 0. I have the point negative 2, negative 2, 0, not negative 3. It's right there. Negative 2, 0. And if you picked a few more points, what you would see is that, again, it's a parabola. And notice every time that we have an equation that has an x squared, we end up with that parabola. Okay, that's just review. Let's go into some new stuff. And this has to do with symmetry. So I'm going to just sketch these. A graph is said to be symmetric with respect to the x-axis if for every point xy on the graph, the point x negative y is also on the graph. And you have a graph that looks kind of like this. It's going this direction. So if I pick a point right here, and I call that XY, it went over however many, and then it went up however many, and that's the point XY. Notice that right across the x-axis from it is the point. It's still over x, but now it's down to get to it, so it's x and negative y. So it is symmetric with respect to the x-axis when it has the point xy and x negative y. Okay, the next one, so let's do this. Let's do symmetric to x-axis. Now let's look at symmetry, or something being symmetric with respect to the y-axis. What that would mean, this is what your graph looks like. I have this graph, and it goes like this. And for every point xy on that graph go across, what would this point be? It would be the point negative xy, because I'm still going up for the y. So that's symmetry, or symmetric to the y-axis. All right, so that's negative x, and that's x, but this is the same distance as that. Finally, we've got symmetry to the origin. And a graph is said to have symmetry or be symmetric with respect to the origin, and it would look like this. Now I'm going to have a hard time drawing this, but not bad. If for every point x, y on the graph, we have the point negative x, negative y. So if I go over here, you can see there's my x, and here is the y. This is the same x in the other direction, the same y in the other direction. So there's tests for symmetry at the bottom of your notes there, and it says to test the graph of an equation for symmetry. We're going to use those three cases. So if it's symmetric to the x-axis, what you do is you replace y with negative y in the equation, and then you simplify. And if you get an equivalent equation, then that graph has symmetry to the x-axis. Okay? All right, to test for symmetry to the y-axis, now we're looking at this sketch. You are going to replace x with negative x and simplify. And if you get an equivalent equation, and I'll show you what that means in just a minute, then we know that the equation is symmetric with respect to the y-axis. Finally, symmetry to the origin, or with respect to the origin, you replace two things. You replace x with negative x and y with negative y. And again, and then you simplify. So let's just try one, and it's easier to see from an example. So let's look at example 7. It says test this equation. Y equals 4x squared over x squared plus 1. And we want to test it for symmetry. So we're going to test it for symmetry to the x-axis. I'm going to make a little chart here. To the y-axis and to the origin. So we're testing for symmetry to all three of those. So this looks like your notes now. So let's see how we do that in a very organized way. So to test for symmetry to the x-axis, go back up here. We replace y with negative y. So go back to your equation, and we're going to take out the y, put in negative y. Does that equal 4x squared over x squared minus 1? Are those two equations the same? No, they're not. One has y, one has negative y, right? So therefore, it's a symbol for therefore, not symmetric to the x-axis. Because when we put in a negative y, we didn't get the same thing we started with. All right? Let's now go to testing for symmetry to the y-axis. So go back up here. Now we're on this one. Replace x with negative x. Okay? Start with your equation. Y equals 4. Take out the x, put in a negative x. Continue to do the rest. Take out the x, put in negative x. So we simplify. Negative x squared is still x squared over x squared plus 1. Did we get the same thing that we started with? Yes, we did. Therefore, yes, it is symmetric to the y-axis. And finally, to the origin, we have to replace both. The x with a negative x, the y with a negative y. So we would have negative y equals, oops, I forgot my 4. 4, I'll squeeze it in, negative x squared over negative x squared plus 1, or negative y equals 4x squared over x squared plus 1. Is that the same as the original equation? No, it's not. So therefore, it's not symmetric to the origin. And it's as simple as that, the test. So to do it, check for symmetry to the x, y becomes negative y. For the y, x becomes negative x. To the origin, y becomes negative y and x becomes negative x. Okay, below here we've got some graphs that you need to memorize. You're going to have a quiz on these. So you've got the graph of y equals x, goes straight through the origin, quadrant 3 up to quadrant 1. Y equals some constant. Y equals x squared. Y equals x cubed. X equals y squared. Let me show you what that one looks like because it's not drawn on there. It looks like this. Okay. Y equals 1 over x. And y equals square root of x. And that one didn't come out very good, so I'm going to redraw that one too. This one is y equals square root of x. It's more curved. It looks more like that. It's hard to see because I used graphing calculator screens on those. You need to memorize those.